Okay, so for this video, we will be discussing uh, the integration technique called trigonometric transformation. So as the topic says, so this will be integrals involving trigonometric functions, and we will use different transformations and different trigonometric identities to convert the integral or the integrand into a form where it can be integrated. Okay, so this will involve several cases, and uh, you need to identify which cases your integrand belongs. So that you can apply the proper transformations and use the proper identities to solve the problems. So the first case is we have case 1, the integral of sine raised to m of x cosine raised to n of x dx. So where either m or n is a positive odd integer. Okay, so either of the two can be a positive odd integer. So what are the positive odd integers? So it could be 1, 3, 5, 7, 9, 11, and so on. Okay, so it says that either. Okay, so when we say either, so at least one of m or n is a positive odd integer. Okay, so the m can be odd, cosine can be even, or m is odd, n is even, or n is odd and then m is even, or m and n are both odd but not both even. Okay, so if m and n are both even, so that will be a separate case, so another case. So if m is odd, so what we're gonna do is take out 1 of sine of x. So this will become sine raised to m minus 1 of x cosine raised to n of x times sine of x dx. So notice, if m is odd, then we took out 1 sine of x. Okay, so what will remain here is m minus 1, and m minus 1 is even. Okay, so we'll then proceed with substitution. So substituting sine squared x is equal to 1 minus cosine squared x. So in this way, we will express the integrand in terms of cosine only, and we have sine x dx that will remain here. Okay, so with that, so on the following examples, you can see that we can solve case 1 using most of the time, most terms we can solve using using the general power formula. Okay, and then there are other terms that we can just apply the integrals of trigonometric functions. So the same if n is odd, so what we're gonna do is we'll take out 1 of the cosine of x. Okay, so n minus 1 here will be even because n is odd, therefore n minus 1 is even, and then we'll substitute cosine squared x is equal to 1 minus sine squared x. Okay, for the even exponent, what do you call that, for the cosine here with the even exponent. Okay, so to illustrate that, so let's have an example. So we have integral of cosine squared t sine to the 5th of t dt. So as you can see, that is case 1. So one of the exponents is odd, a positive odd integer. So we can see here that it's, so this is m. Okay, so the exponent of sine, so m is equal to 5. So the odd exponent, so we will separate 1 of sine t, so that sine, the exponent of sine will be even. Okay, so this will become integral of cosine squared of t sine to the fourth of t and sine of t dt. Okay, so notice we factored out 1, no, sine t from sine to the fifth of t. So what will remain is sine to the fourth of t, and then the factored out sine t here. Okay, so we will now replace. Okay, so this is case 1. So we will now replace sine squared x with 1 minus cosine squared x. So here we can't see any sine squared x. Okay, so but there is actually, so this can become cosine squared of t, okay, multiplied by sine squared of t squared sine t dt. Okay, so sine to the fourth of t is equal to sine squared t squared. Okay, so with that we can now substitute this. So this will become integral of cosine squared of t multiplied by sine squared of t is 1 minus cosine squared t. So 1 minus cosine squared of t, okay, squared, and then sine of t dt. Okay, so next what we're gonna do is expand this square of a binomial. So we have integral of cosine squared of t. So this will become 1 minus 2 cosine squared of t plus cosine to the fourth of t, and then sine of t dt. Okay, okay, so the next is we will distribute, no? So we can distribute cosine squared of t and sine t dt for each term. So this will become, so the first one, cosine squared t times 1 times sine t dt. So that is integral of cosine squared of t sine of t dt, and then cosine squared of t times negative 2 cosine squared of t times sine t dt. So we have here a numerical coefficient of negative 2, so we can take that outside of the integral sign. So minus 2 integral of, so we will have cosine to the fourth of t, and then sine of t dt. Okay, so the last one, so this will become cosine to the sixth. Okay, so this can now be integrated by using the general power formula. So each of the terms can actually be solved using the general power formula with our u as cosine of t. Okay, so therefore our du should be, it should be negative sine of t dt. Okay, so therefore we have a missing negative now in the factors, so this will become integral of cosine squared t. This should be negative sine t dt. Okay, since we place a negative sign beside this, the sign of t, then outside the integral sign we will also put negative. Okay, so plus, oh sorry, so that's minus minus 2, okay, minus 2 integral of cosine to the fourth of t, and then we will place negative for sine. Since we put here negative, so this will become positive. Okay, then the last one, so plus integral of cosine to the 6th of t, and then negative sine of t dt. Then we will also place a negative sign here. Okay, so therefore using the power formula, so this will become negative, so u raised to n plus 1 over n plus 1. So this will become, so our u is cosine of t raised to n plus 1, so n is equal to 2, so raised to 2 plus 1 over 2 plus 1. Okay, plus 2 times, so power formula again here, so we have cosine of t raised to 4 plus 1 over 4 plus 1, and then minus power formula on the third term is cosine of t raised to 6 plus 1 over 6 plus 1. And then we have finished integrating, so therefore plus c. Okay, so therefore the integral of cosine squared t sine to the 5th of t dt is equal to, so this will become negative 1/3 cosine cube of t plus, we have here 2 over 5, so 2/5 cosine to the 5th of t minus 1 over 7 cosine raised to 7 of t plus c. Okay, so that is how to use the so that is how to solve integrals involving case 1. So for trigonometric transformation, still on trigonometric transformation, we have case 2 for the integral of tangent raised to n of x dx, or the integral of cotangent raised to n of x dx, so where n is an integer. Okay, so any integer. So use the identities tangent squared of x is equal to secant squared of x minus 1, and or cotangent squared x is equal to cosecant squared x minus 1. So obviously, so these are even, no? So squared and squared. So if n is odd, then we'll have to make way for it. We'll have to do something, no, for the for the exponent, so that it can be expressed as even, and then we can use these identities. So say for example, we have the integral of cotangent to the 5th of 2y dy. So obviously it's this one, and then we're gonna be using this one. Then since this is squared, so we cannot use this here because this is odd, so therefore we will separate one of the cotangent 2y. So this will become integral of cotangent to the 4th of 2y times cotangent 2y dy. Okay, and then this cotangent to the 4th, no, is also equal to cotangent squared of 2y squared, okay, times cotangent 2y dy. Okay, so replacing cotangent squared with cosecant squared minus 1, so this will become integral of cosecant squared of 2y minus 1 squared times cotangent of 2y dy. Okay, so next thing to do, expand this, so this will become integral of cosecant to the fourth of 2y minus 2 cosecant squared of 2y minus 1 times cotangent 2y dy. Okay, so the next is we will distribute, so this will become integral of cosecant to the fourth of 2y cotangent of 2y dy minus, so we have a numerical coefficient here of 2, so minus 2 integral of cosecant squared of 2y and then cotangent of 2y dy. Sorry, this should be plus, not from this expansion, so plus integral of cotangent of 2y dy. Okay, so we can solve this using, so the first two terms are the general power formula. The integral of cotangent here is simply ln of sine. Okay, so but we must identify first our u. Okay, so if our u here, obviously we have raised to the power of 4, so this probably must contain our u. So if our u is cosecant of 2y, its du should be the differential of cosecant. So the differential of cosecant is cosecant cotangent, and here we only have cotangent. So therefore, we must separate one cosecant 2y from cosecant to the fourth of 2y so that we can complete the differential. So this will become integral of cosecant cube of 2y, okay, times cosecant 2y tangent 2y dy. Okay, so similar here, so separate 1 cosecant 2y, so we have 2 integral of cosecant 2y times cosecant 2y cotangent 2y dy. Okay, plus retain integral of cotangent of 2y dy. Okay, so here we can now have our u. So our u is cosecant of 2y. So this is for the first term and the second term. So if our u is cosecant 2y, so therefore our du should be, the differential of cosecant is cosecant cotangent. Okay, and then by the chain rule, so we still have to multiply it with the differential of the function, no, inside cosecant, so multiplied by 2 dy. So therefore this will become, so sorry, the differential of cosecant is negative cosecant cotangent. Okay, so du will be negative cosecant 2y cotangent 2y multiplied by the differential of 2y, which is 2 dy. So our du should be negative 2 cosecant 2y cotangent of 2y dy. Okay? And also here, so if you recall our integral of cotangent, so integral of cotangent u du is equal to ln of sine of u. Okay? So but the du should be the complete differential of u. So our u here is 2y. So therefore, our du should be 2 dy. Okay? So to apply this formula, so we must put here 2 beside dy. So therefore, so completing the differentials, so this will become equal to integral of cosecant cube of 2y. So there should be a negative 2. Okay? So negative 2 cosecant 2y cotangent of 2y dy. Okay? So for the second term, so we actually already have negative 2 here. So all we can what we can do is we can take it back inside the integral sign, or we can just add negative 2 in here and then multiply by negative 1/2 outside. So it's your call. So to save space, so I want to just transfer the negative 2 back inside the integral sign. So we will have plus integral of cosecant 2y and then negative 2 cosecant 2y cotangent 2y dy. Okay, so the negative 2 outside, so I placed it back inside the integral sign. Okay, so plus the integral of, so you have here cotangent of 2y. So the complete differential should be 2 dy. So since I placed 2 here, then outside the integral sign I will put its reciprocal, 1/2. Okay, so I'm sorry I made a mistake. So going back here, so since we placed negative 2 here, okay, so I forgot to place the negative reciprocal outside the integral sign. So there should be a negative 1/2 here. Okay, so from here, so to complete the differential, we place negative 2 here. So therefore, outside the integral sign, we will place the negative reciprocal of negative 2. Okay, so with that, so let's now proceed with the general power formula. So this will become negative 1/2 multiplied by, power formula, so u raised to n plus 1. So our u is cosecant of 2y. So therefore, we will have here cosecant of 2y raised to 3 plus 1 over 3 plus 1. Okay, so plus, so power formula again for the second term. So our u is still cosecant 2y. Our n in here is equal to 1, so therefore raised to 1 plus 1 over 1 plus 1, and then plus integral of cotangent 2y is ln of sine 2y, and then we have here 1/2, so 1/2 ln of sine 2y, and then plus c. Okay, so therefore this will become Negative 1 half times 1/4, so this will become negative 1 over 8. Okay, cosecant to the fourth of 2y plus 1 half cosecant squared of 2y plus 1 half ln of sine 2y plus c. So this is now our final answer. Okay.